Hello. So in this one we are going to solve a bunch of problems using chain rule as we have discussed, and we are going to essentially understand how to use the chain rule in terms of differentiation. So it might be a long ride, but as I already said before, this is how we are going to learn several variable calculus to use for in the probability and statistic courses and in the upcoming courses as well. So the chain rule that I have told you for using in multivariable calculus was a bit different than that of the old chain rule we used for single variable calculus, but it makes sense if we want to merge the two, right? So in light of the previous chain rule, we are going to give you a few more examples of how to use it. So let me write down a corollary first. So if f and g are functions from r to the power n to the real numbers and are differentiable at some a belongs to r to the power n, then the following also hold. It proves that the differentiation is also a linear operator, as we already know that differentiation itself is a linear operator, because as we have seen before, the derivative of a multidimensional function is basically a linear transformation which goes from the same dimension to the same dimensions, and that is how we find the answer, right? So in case of summation, it's pretty simple. We can do it plus minus as well. In case of multiplication of two functions, let's say, or composition maybe, so if you are going to multiply f into g, we can write this as g of a into df of a plus f of a into dg of a. So this is how it works. Moreover, if g of a is not equals to 0, we can also define the division as before, like this. We can find g of a whole squared, and we can write g of a into df of a minus f of a into dg of a. So this would give us the rule for the differentiation. So like these are the problems that we are trying to do here, and this is something that we would try to understand in the coming lectures on how to find out these properties, how to do them, and things like that. So let us start with a few examples, and we shall see how to do those examples one by one. Example 1. So let f be a function from r squared to r, and we can find that since f is a function from r squared to r and it is defined by f of x comma y, so it's a two-dimensional function given by sine of x y squared. Okay, so find df of a comma b. So we need to find the derivative at the point a comma b. Well, firstly, in this cases we obviously assume that the derivative exists, and we are going to find it by the chain rule, and it does exist because we are just finding a general derivative. We are not really proving differentiability under any condition, and we know that the function sine and the function x and the function y square, all of them are differentiable, and composition of differentiable functions are differentiable as long as they are also in the domain. So this is pretty much how it works. So solution. Now, as we did in chain rule, in this cases, in this kind of scenarios, what we are going to do is we are going to define linear transforms. So first let us define some linear transforms for the sake of this problem and for the others. So what I'm going to define here will be applicable to everything else. So define pi I as the vector 0 comma 0 comma dot 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 I at the ith place and zeros again. Okay, so this is pi I, and also define that pi I prime is basically equals to pi I. This is from the example we did before, that if lambda is a linear transformation, then d lambda is basically equals to lambda. So the derivative of a linear transform is the linear transform itself. So taking that into account, what we can do here is as follows. We are going to define the function f in a certain way. We are going to define it as f of x comma y, which was given as sine of xy squared, and we are going to define this as the composition of sine composed with xy square. We are going to define as pi 1 for x. So we have three variables, and we are going to define it as like this: pi 1 into pi 2 squared, and we are going to implement AB, right? So the derivative f dash AB according to the chain rule should be, firstly, inside sine we find out the derivative of sine, and we can find out pi 1 into pi 2 squared. Let me just write it down cleanly, because this wouldn't make much sense if you do not understand it. If I do not write it clearly, it will be of no use. So what I am trying to say here is we can write it as sine, this is the derivative of sine, and the argument is basically pi 1 into pi 2 squared at the point a comma b, multiplied by, this is the first part of the chain rule where you differentiate the first function, and the argument is basically the second function. And now we differentiate the second function, which is pi 1 into pi 2 squared derivative at the point a comma b. Okay, firstly we know that since the derivative of sine is cos, we can simply write cosine and put in the values of a and b. Here it's ab square. So this is the first part, and it is multiplied by pi 1 pi 2 squared derivative at a comma b. Now this is the product of two functions, and we learned how to do them. It doesn't matter, because pi 1 pi 2, these are all two-dimensional vectors, but it does not matter because we have learned in the just now that we can do this summations and products and all of these things, right? So what we can do is this: we can find out this as pi 1 prime into pi 2 square at the point ABC, AB, and then again pi 2 squared differentiation multiplied by pi 1 at the point a comma b. This would mean this is cosine of ab squared multiplied by, now pi 1 prime is just pi 1, and this pi 2 squared is basically b squared. You just put in the value b squared, and pi 1 prime is the it's not 0 actually, sorry, it's 1 comma 0. So it's basically pi 1 prime is 1 comma 0 multiplied by pi 2 square, and you put in the value, you get it as b squared, plus pi 2 primes is basically 2 pi 2 into pi 2 prime into pi 1 a comma b. I'm going to do that in the next step. So this is cosine of ab squared, and this is basically b square comma 0 plus 2 pi 2 pi 1. On putting the value, you get 2ab, and pi 2 prime is simply 0 comma 1, right? Because it's a two-dimensional vector. This is because we have two variables, right, x and y. That is why what we are taking the linear transform, these are two variables. The basis is the basis pi 1 and pi 2 and up to pi n are basically defined by the domain, which is r to the power n. So here the domain is r squared, so we are taking 1. So this becomes cosine of ab squared, and same dimensional vectors add up, so we have b square comma 2ab, and if you multiply in the cosine part, what you get is this: you get the answer as b square cosine of ab square comma 2ab cosine ab squared, which is the answer. So in a similar way we can do a lot of other problems, but understand what we did here. This is how it works. Okay, so let us move on to next problem. Example 2. And in the midst of these examples you will see a lot of parts where we are going to remind to you. So in every video, whenever we are doing examples, I'll give you a review of how the chain rule works, and the chain rule video would be included, along with maybe some of the videos from multivariable calculus itself, just to give you a prerequisite, so you can either skip it or you can just revisit it for 10 to 15 minutes so that you understand this part. So what we actually want is, we do not want you to get scattered while watching a particular video, because videos are usually long and they're very much in depth. So these problems which we are solving, they might require a lot of special tools which you might have forgotten, which you might remember. So in case you have forgotten, you can just go back into the same video without changing the video to see whatever you require, and that is how we make sure what to put extra in the video, so that you can go back and check and then come back again. Anyways, so example 2. So this is another example where we have a function from r cube to r defined by x to the power y. So find d of abc. First of all, notice that it has 3 inputs, so the linear transform would be 3 dimensional. So all the basis for r cube is 0 0 1, right? 0 0 1, 0 1 0 and 1 0 0. These are the basis operators for the Euclidean space r cube. Now write f of x y z as this. We can write this as x to the power y, which is basically e to the power y log x, which is basically exponential pi 2 into log of pi 1 at the point x y z. So therefore the derivative would be something like this. Firstly, we would be doing exponential's derivative at the point pi 2 log pi 1 at the point a b c multiplied by pi 2 into ln of pi 1 derivative at the point a b c. This would give us, since the derivative of exp is just exp, it's basically e, and if you put in the values of a b c, after that e to the power pi 2 log pi 1 would become e to the power b log a, and what we are left with is this. We are left with pi 2 log of pi 1 prime a comma b comma c, right? This becomes a to the power b, and now this is a product for two functions, so obviously it would be pi 2 prime into ln of pi 1 of abc plus ln of pi 1 prime into pi 2 into abc, right? So this becomes a to the power b, and now pi 2 prime, as I told you, it's 0 comma 1 comma 0, right? Ln of pi 1 just becomes ln of a, putting in the value, and this becomes ln of pi 1 prime is just pi 1 prime by pi 1 into pi 2 at the point abc, because ln of x is just ln of f of x is basically f dash x by fx, right? So that's just a single variable calculus task. So a to the power b, multiplying this you get 0 comma ln of a comma 0 plus pi 1 prime is basically 1 comma 0 comma 0, and pi 2 by pi 1, when putting the value you just get it as b by a. So it becomes, on a to the power b, and in bracket it becomes b by a ln a comma 0, and thus multiplying the constant a to the power b inside the vector, we get the ultimate derivative as a to the power b minus 1 into b a to the power b into ln a comma 0, which is the answer. and you can check it's basically a 1 cross 3 matrix, which should be the answer because the function was from r to the power 3 to r to the power 1, right? And it makes sense. Okay, let us do another one. So example 3, given f of x comma y equals to sine of x into sine y, find df at the point a comma b. Well, it again is a two-dimensional function, and let us begin. We can see that f of x comma y can be written as composition of sine multiplied by, now this is something which cannot be written directly, but well, it can be written as pi 1 into sine of pi 2 at the point x comma y for now. So therefore the derivative is df a comma b is basically sine's derivative at the point pi 1 sine pi 2 at the point a comma b, and multiplied by pi 1 sine pi 2 derivative at the point a comma b, right? Well, sine's derivative is cosine, and putting the value you get cosine of a sine b, and this one now pi 1 into sine pi 2 is just a multiplication, so it is basically pi 1 prime into sine pi 2 at the point a comma b plus pi 1 into sine pi 2's derivative at the point a comma b. And these are like relatively simple once you understand the concept, because the derivative of the linear transforms are the one basically giving you the vectors. Okay, here the vectors are like 0 comma 1 and 1 comma 0, and whenever you have something linear transform in a function or itself without the derivative, it is just a matter to put the value inside, the corresponding value inside that, right? Like it is pi 2, so it should be b, because pi 1 corresponds to a, pi 2 corresponds to b, pi 3 corresponds to c, and so on. So this is cosine of a sine b, and this is basically 1 comma 0 times sine b, right? Similarly, this sine pi 2's derivative is pi 2 prime into cosine of pi 2. So it is basically pi 2 prime into cosine of pi 2, and we also have a pi 1 separately at the point a comma b. This would give us cosine of a sine b. We have sine b comma 0, and pi 2 prime here basically is 0 comma 1, and this is cosine of b into a. So all in all, what we do have is this cosine of a sine b, and we have this as sine b comma 0 plus 0 comma a cos b. Adding them together, we get cosine of a sine b multiplied by the vector sine of b comma a cos b, and multiplying everything together we get sine b cosine of a sine b comma a cos b cosine of a sine b, which is our answer. So this is a 1 cross 2 matrix, as you can check, which is the answer. So yeah, like these are the questions, and these questions can be solved easily, if not very tough, but well, we would need to do some exercises to solve them. Okay, let's move on to another example to see how this works perfectly. Example 4, given this one is a bit more complicated, but well, knowing all the rules, I do not think it would be much of a problem to solve them. So this one is sine of x sine of y sine z. Okay, so the first sine bracket closed, second sine bracket closed. We need to find the derivative, of course, at the point ABC. So we can write f of x comma y comma z as the composition of sine with pi 1 sine of this should be pi 2 sine pi 3, right, at the point A comma B comma C. Well, so the derivative is df of A comma B comma C is sine in the point pi 1 sine of pi 2 sine pi 3. So sine 1 into pi 2 sine pi 3, and this is at the point ABC multiplied by pi 1 sine of pi 2 sine pi 3 at derivative at the point ABC. So let us evaluate this first part as in the first sense. It's basically cosine of A sine of B sine C, and multiplied by, let this function be written as g of ABC, g prime of ABC, right? So define g of xyz as, so we are going to define this argument completely differently, x into sine of y sine z. This needs to be removed. Sine of y sine z, right? Now this is basically x multiplied by sine of, we can write it like this, sine of pi 2 sine pi 1 pi 2 sine pi 1, and this could be written in the point A comma B comma C, like that. So anyways, since it's a product of two functions, we can write it as g prime ABC is basically x prime at the point ABC. So it's basically x prime at the point ABC multiplied by this sine of pi 2 sine pi 1 at the point ABC, plus what we can write here is x into sine of pi 2 sine pi 1, this derivative at the point ABC, right? So like this is how this thing works, and we can surely write that in terms of it. So the first one gives us, since x prime is basically pi 1, we can say, because x is basically pi 1, so what we can do is we can write 1 comma 0 comma 0 times sine of b sine a. It was actually z, right? So it should be pi 3 b sine c, plus what we can do is a times sine of pi 2 sine pi 3 whole derivative at the point A comma B comma C. Now let us evaluate this separately. Let us evaluate that sine of pi 1, is it pi 1? It's pi 2 actually. Pi 2 sine of pi 3, this thing's derivative at the point A comma B comma C, right? What we can do here is as follows. Obviously, using the chain rule, this should be sine derivative of pi 2 sine pi 3 at the point ABC multiplied by, we still have the derivative of pi 2 sine pi 3 derivative at the point ABC, right? Now this is basically cosine of b sine c multiplied by, now pi 2 sine pi 3 would be just pi 2 prime into sine pi 3 at the point ABC plus pi 2 into cosine of pi 3 into pi 3 prime at the point ABC. Okay, so this gives us cosine of b sine c multiplied by, now pi 2 prime is just 0 comma 1 comma 0 into sine c, and this is basically b cos c into 0 comma 0 comma 1. So this gives us the vector 0 comma sine c into cosine of b sine c comma b cos c into cosine of b sine c. So this is what the derivative looks like, and thus g prime ABC would be something like this. Therefore g prime of a comma b comma c would be, so you see 1 comma 0 into sine of b sine c, so it basically is sine of b sine c comma 0 plus, that's the first part, plus you have a into this thing, right? So plus what you have is this 0 comma a sine c cosine of b sine c comma ab cos c into cos of b sine c, and together we have g prime ABC as sine of b sine c comma a sine c cosine of b sine c comma ab cosine of c into cosine of b sine c. This would be g prime of ABC. Now we go back to our original problem. It was cosine of a sine b sine c into g prime ABC. So therefore df of ABC was just cosine of a sine of b sine c multiplied by g prime of ABC, and this would give you the answer as sine of b sine c into cosine of a sine of b sine c multiplied by a sine c into cosine of b sine c into cosine of a sine b sine c comma, and the last part is ab cosine of c cosine of b sine c multiplied by cosine of a sine b sine c, which is the answer. And that would conclude the problem. So you would see a lot of chain rule theorems and problems included in the video as well in reference to this, and in the next one we shall also find out about more. intriguing examples. Let us begin with the chain rule. The chain rule states that the derivative of a composite function where f of x is continuous for all x belongs to u, where g is a function such that it goes from d to u, and g is continuous and differentiable at x belongs to d, then the derivative of the function f of g of x is given by f dash of gx multiplied by the derivative of gx. So it might look that it's not such a big result, and okay, the definition might be a bit more complex, but the result itself says that the ddx of f of gx, considering all the other technicalities solved, that f is continuous at g of x and f is differentiable at g of x and g is differentiable, we can say that the function f of gx can be differentiated by just differentiating the function f at the point g of x and then just differentiating g of x at the point x and multiplying them together, right? But this simple definition is the key to solving all of derivatives problems, as you can see now. So if you remember the basic derivatives, which I can recall one by one, it's like x to the power n is n into x to the power n minus 1, sin x is cos x is minus sin x and stuff. Then logarithm of x is 1 by x, e to the power x is e to the power x itself. Now we can try and find out the derivative of. So we are going to do a bunch of problems now. So let us do ddx of e to the power ax. So ddx of e to the power ax. So first recall the basic function. The function, what it starts with? It starts with the function e, right? E to the power something. Now what is the most basic representation? It's e to the power x. So if you remember, ddx of e to the power x was e to the power x, right? So we are going to copy this and write the answer itself. That is, the answer should be whatever is given. So e to the power ax, right? So pretend as if this function was e to the power x only and write the whole function down, but then multiply it with, go to the next level of the function where the anomaly is present. So it should have been e to the power x, but it isn't, right? What is there instead of x? It's a of x. So now it should be ddx of ax, where a is just a constant, and when you do a constant x, a times x, the ddx of x is just 1 and constant just comes out. So the answer becomes a into e to the power ax. This is because ddx of x is just 1, and also ddx of a constant c times any function f of x is just c times the derivative of the function. So the constant just remains multiplied throughout. Okay, next example. Because the more examples we do, the more it would be easier for you to understand. ddx of ln of, let's say, x squared. So how do we do this? Well, first we try to think what the ddx of ln of x is, because the first function is ln of x, right? So ddx of ln of x is equals to 1 by x, right? So pretend as if this function is ln of x, and we write the derivative as 1 by x square. So do not directly write 1 by x, because you just need to pretend. But when you are going to write the derivative, you are going to write the same thing, and instead of x, whatever is present, you are going to use that. But you're just pretending it is x, right? Now you multiply and you do the derivative of the next level, the expression which is present instead of x. So x square is present here, so we do x square. So it is 1 by x square into ddx of x square by the rule for differentiation of powers is 2 into x to the power 2 minus 1, right? So it will become 1 by x square into 2x, which will give you 2 by x, right? Okay, one more. Let us try to evaluate ddx of log of sin x. Now, how many layers are there? Let me just clarify this like this. Layer 1 is the first layer of function. This is log. So layer 1 is log x. And what is layer 2? Layer 2 is sin x, correct? So it is log x and it is sin x. Now, the answer can be written directly if we have that in mind, because we differentiate one by one, and we keep on doing that until we reach the inner bottom where x is present. So ddx of log of sin x is simply equal to, firstly we do the ddx of log x, which is 1 by sin x, and then we do the differentiation of sin x, which is cos x, right? And cos x by sin x is simply cot x. So you see, we have got the answer. ddx of log sin x is just cot x. Okay, so this is not really a very hard one to be done. Let us move to other examples. We need to find the derivative of this function. So here comes the harder ones, or rather you can say the more complex ones, because if you know what to do, I do not think this would be at all hard for you any more than it for the last problem was. But then again, this would be a bit more calculative, right? So we first need to understand the layers and stuff. So what is layer number 1? Layer number 1 is of course sine of x, right? Sine and some x inside it, which we are going to pretend is x. Layer 2 is of the form fx by gx, right? Layer 2 is of the form fx by gx, which we learned before, that the derivative of two functions can be evaluated how? I'll just write it down here, that ddx of fx by g of x can be evaluated as fx into g prime x, right? What is layer number 3? So in fx there are two layers, right? In fx there are two layers. How many layers are there? Fx has a layer which says that the inside function is x square plus 2. Similarly, gx has a layer which says that the inside function is e to the power 5x plus e to the power x, right? But these layers do not really matter, because we already have a fx by gx thing here, right? So we are going to use them here directly. So let's do this. Let us first define the function as capital F of x equals to sine of, let me just copy it, log of x square plus 2 divided by e to the power 5x plus e to the power x. e to the power 5x plus e to the power x. Then f dash x would be, so firstly the derivative of sin x is cos x, so we first have this right, multiplied by, now we have the part where we do actually fx by gx thing. So this is gx, this is fx, so this should be squared. Squared means multiplying by 2 in the power, which is e to the power 10x plus 2 e to the power x. Then we have e to the power 5x plus e to the power x into the differentiation of log of x square plus 2. So first we pretend it's a log of x, so we do a by x square plus 2, and then we do the inside, which is x square plus 2, differentiating which you get 2x, because the differentiation of a constant is 0, and if you remember, addition of two functions when differentiated is basically equal to derivative of the first function plus derivative of the second function. So here derivative of the constant is 0 and derivative of constant of x square is 2x, so 2x minus ln of x square plus 2 plus remains like that. And now we do the exponential. So firstly the exponential remains the same, so it's e to the power 5x plus e to the power x multiplied by, we do the 5x plus e to the power x, which is 5 plus e to the power x, so 5 plus e to the power x. So we can write it clearly here, cos of ln of x square plus 2 by e to the power 5x plus e to the power x multiplied by, now we can do a simplification here, x square plus 2 into e to the power 10x plus 2 e to the power x, and we can write it as follows: e to the power 5x plus e to the power x taken common, we have 2x minus x square plus 2 into ln of x square plus 2 into 5 plus e to the power x, and we can cut off this 5x plus e to the power x and this to give you the final answer, which is cos of ln of x square plus 2 divided by e to the power 5x plus e to the power x into 2x minus x square plus 2 into 5 plus e to the power x into ln of x square plus 2 whole divided by e to the power 5x plus e to the power x into x square plus 2. So this is our final answer, and obviously some multiplication in between. So this is our final answer for the problem. So it's time to prove two of these things. So proof 1, we are trying to prove that limit x tends to 0 ln of 1 plus x by x is equal to 1. Okay, see, this is not a very easy proof, but we can walk our way through it. I'll just show you how. Well, first of all, x tends to 0, so this obviously means that we have that mod x less than 1, since x tends to 0, so x is in the close neighborhood of 0, right? So it's like an epsilon distance, which is very small, we can consider as small as we want to be, and it's in that distance in between 0. So basically x lies in an interval like this, where minus epsilon to plus epsilon, and epsilon is sufficiently small right? So with this expression in mind, what we can do is we are trying to find a series representation for logarithm of 1 plus x, natural logarithm in fact. How do we do that? Not yet, but let us try to use the theory we have used earlier, which is the Taylor series, right? But in this case we need to find it near 0, so we can use the Maclaurin series directly. We remember that Maclaurin series for fx is given by f of x is equals to summation n equals to 0 to infinity nth derivative of f at the point 0 divided by n factorial into x to the power n, right? And here we have mod x less than 1, since we are trying to find it for logarithm of 1 plus x, which is only defined for minus 1 less than x less than 1. Okay, so the only term we need to find is the nth derivative at the point 0. So let us begin and try to see what happens. So firstly, f of 0 should be ln of 1 plus 0, which is ln of 1, which is 0. So the first term is 0, like the 0th term is 0. Okay, f dashed x in fact would be 1 by 1 plus x, and this would mean f dashed 0 should be 1, right? F double dashed x would be minus 1 by 1 plus x whole squared. So f double dashed 0 should be minus 1. Again, f triple dashed x should be 2 by 1 plus x whole cube, and this would mean that f30 is 2, right? So this is going to give us a pattern very soon if we just continue it for like 3 to 4 terms, because I do not really want to indulge you with the nth derivative formula directly, which we can calculate directly from here, but let's save that for the derivative portion. So f4 of x again would be minus 6 by 1 plus x whole to the power 4, or in other words this is just minus 3 factorial by 1 plus x whole to the power 4. So this was give us f40 equals to minus 3 factorial. Let us do 2 more terms. f5x would then be the differentiation of this, which would give you another minus, it will make it a plus, and it will be 4 factorial by 1 by x to the power 5, which would give me f5 of 0 equals to 4 factorial. And similarly f6 of x should be minus 5 factorial, judging by it should be minus 5 factorial by 1 plus x whole to the power 6, and this should be equals to minus 5 factorial, right? So as you can see, for the even order of derivative, we have a negative factorial, 1 less than it, and for the odd we have the positive factorial but 1 less than the derivative. So we can write that ln of 1 plus x, by the Maclaurin series definition, it should be f0 plus x into f dash 0 plus x square by 2 factorial into f20 plus x cube by 3 factorial into f30, and so on, right? Now once we start putting in the values, we see that f0 is 0 and f dash 0 is just 1. For the even one it's negative, if you remember, so it's not plus, it's like minus x square by 2 plus x cube by 3 factorial into 2 factorial minus x to the power 4 by 4 factorial into 3 factorial, and so on. Remembering that 3 factorial is just 3 into 2 factorial, so the 2 factorial will cut off and 3 will remain. Similarly here 3 factorial by 4 factorial will give you a 1 by 4. Continuing in this way, we get the series as x minus x square by 2 plus x cube by 3 minus x to the power 4 by 4 plus x to the power 5 by 5 and so on. So this basically right here is the Taylor series expansion for log of 1 plus x at the point x equals to 0. Now we want to see that in the limiting case we were trying to prove that limit x tends to 0 ln of 1 plus x by x, right? Now let us write it under, because the series could be a long shot, so we can use the series definition here and we can write it as 1 by x into x minus x square by 2 plus x cube by 3 minus x to the power 4 by 4 and so on. Now since we know that x tends to 0 means x is not equal to 0, we can divide by x and we can find that the answer is 1 minus x by 2 plus x square by 3 minus x cube by 4 and so on, right? Now as I know that we can always put the value of the limit whenever the function is defined, here we just have a bunch of plus and minuses, obviously infinitely many of them, but we can write this as 1 minus limit x tends to 0 and then x by 2 minus x square by 3 and so on. Okay, but all of these terms will be 0 because when you put in x equals to 0, doesn't matter how many of them are infinitely many zeros add up to zeros only, so the answer would be just 1 minus 0, or which is 1, and thus we have proved our limit. Thank you for watching. So please download the Breatter Maths app, which is given in the description. It is a mathematical app where you can find all the necessary statistical calculators like chi-square calculator, one variable means, population means, t-value and much more. You can also find calculus related calculators like integration, derivatives. There is a section where you can find what's coming up next. There is a section completely devoted on mathematical notes where you can find notes on probability, statistics, calculus and many more are there to come. In those notes we have already explained all the examples, all the problems and theory, and we are just covering the video lessons and solutions of those here. You can check that out. Also you can see the video solutions in a separate section where you can understand and give a feedback on what to expect next. You can ask for a problem, you can ask for a theory section as well. So please do check it out, and also do subscribe to Breatter Maths app and also its YouTube channel.